My name is Victoria and I'm working at FimeTech as a machine learning engineer. So today I'll talk about speech recognition techniques with especially hybrid models. Recently at FimeTech we started to work on speech recognition. Our goal is to have speech recognizer with streaming mode and it should run on embedded devices. It's a hard problem and it gets harder, even harder when the embedded devices have limited capabilities and they also have strict power requirements. So how we should achieve our goal? At first we started to look at the state-of-the-art models, but soon we realized that it's not our case and what should happen if we tried to run these models on our devices. The result should be something like this. So this is not our direction and we start to do more research and dig deeper. And I'll start from the very beginning, the history of speech recognition, and then I'll talk about traditional speech recognition techniques, the hybrid end-to-end models, their pros and cons, challenges that we have faced, and finally, our approach. So we'll start with the history. The first speech recognition techniques were focused on numbers, not words. The first system was in 1952. The Bell Laboratories introduced the Audrey system. It could recognize a single spoken digit. So the technology was quite simple. They were trying to match the filter bank output to hand-constructed templates. 10 years later, IBM introduced a new system that could recognize 16 words in English. In the 1970s, Harpy system came out, and this could recognize 1,000 words. This number of words is about the same as 3-year-old's vocabulary. So the 80s saw speech recognition going from a few hundred words to 1,000 words. And one of the breakthroughs was because of the statistical method known as the hidden Markov models, the HMMs. So instead of looking for words and using the sound patterns, HMMs trying to estimate the probability of unknown sounds actually being words. In the mid-80s, HMM-based technology started to be widely studied and applied in speech recognition. It was during the time that Sphinx came out. This is a combination of hidden Markov models and Gaussian mixture models. So hidden Markov models are trying to estimate the probability of ones, and using the GMM models, Gaussian mixture models, this made a breakthrough and considered a milestone for a long time. Until deep learning applied, these HMM, GMM-based technologies were considered the dominant framework for speech recognition. During the 90s, speech recognition moved forward because of personal computers and faster computations. During this time was introduced a dialing conversational speech recognition system, and this system was important because it gave birth to a system technology that is phone trees. We'll speak about them later. In 2001, speech recognition had achieved close to 80% accuracy. This is really good, and the early part of the decade were not much advancements until Google appeared with the launch of Google Voice Search. As this was an app, this put speech recognition into the hands of billions of people. Google started collecting data, and it helped to understand better what a person is actually saying. During this time in 2011, Apple launched Siri, and the decade was full of this kind of technologies. And with Amazon's Alexa, Google Home, we've seen consumers started to become more and more comfortable talking to machines. And the biggest advancement during this time in 2011, Microsoft Research Institute proposed a new way, a combination of hidden Markov models and neural networks. These were a big step forward and was considered a new milestone in large vocabulary continuous speech recognition. After this, neural networks started to be widely applied in all the systems of speech recognition. Traditional speech recognition techniques. Let's define the task of speech recognition. It is building a statistical model to infer the text sequences from audio sequence, feature sequence. So the traditional systems look like this. It's very complex, but it mainly consists of an acoustic model, a language model, and the lexicon. We'll speak about each of them one by one. But first we need features from the audios. Starting from the audio clip, we slide over it and extract features. Actually, this is the first step in speech recognition, and different algorithms can be applied to get the features. The most commonly used one is the male frequency cepstral coefficients, the MFCCs. The acoustic model. The acoustic model is about modeling the feature vectors from the sequence of phones or words. So the traditional way is to use Gaussian mixture models to get the features of phones and the probabilities of those features. The next one is the language model. It's about the likelihood of a sentence, the sequence of words. The most simple one is to calculate the probability of word given the previous word. So it's called a bigram system, and when you use the generic way and you look for n neighbors, it's called n-gram language model. So actually this is the functionality of language model. The next thing is the lexicon. These lexicon files are created to help to understand how phones should be connected to create the word. So these lexicon files are created by linguists mainly. So these are the main components of traditional speech recognition systems. And going back to the objective of speech recognition, we need to get the maximum probable word sequence from the feature sequence. And applying bias rule from the next line and removing the probability of features, because they are not changing with respect to words, we get a formula that is multiplication of two models, the acoustic model and the language model. So this approach may sound indirect and not inefficient, but it's all about how we can model this. The probability of features given words is much easier to model in speech recognition. We can use Gaussian mixture models to model the feature vectors probability distribution for a phone. And we can also use hidden Markov models to model the transition between the phones and the observables. So the hidden Markov models consist of hidden variables and observables. The hidden variables are the states and the phones that we are using to model the speech, and the observables are the audio frames that we calculated for the first. And using this mechanism, it's not that much bad. We don't need to search the phone sequence one by one, otherwise the complexity will grow exponentially. We can use, in this modeling with HMMs, we can use algorithms like Viterbi to get the optimal sequence in polynomial time. And other key ideas, and it's very important, the phone representation. As we are trying to represent our speech with phones, we need to represent it good. So phones are not homogeneous, and amplitudes of frequencies change over time, and we can see even from the spectrogram that the beginning, the middle, and the end of the phone differs. And we need to subdivide a phone in these three states to get a better representation. Also, sounds change depending on their context, the neighbors. And these neighbors affect phonetic variability a lot. For example, if we put our hand in front of our mouth, we will feel the difference when we pronounce P for spin and P for phone. You can try it also and see the difference. And to get a good acoustic model complex, we need to take into account all these states. So it's all good. We are getting important information with these divisions, but the number of phones become non-manageable. So we need to not treat the phones independently. When we treat them independently, it's called monophone system. This is the simpler version, and we can also use other systems. And when we take the left and right context, the two neighbors, it's called triophone system. And with these divisions, we get more and more triphones that are non-manageable for HMM states. But fortunately, some triphones are hard to distinguish even from this spectrogram. So there are phones like that we can group together and have a new group of triphones. So for this, we can use decision trees. This is technique when we want to make clusters of similar phones and treat them as one phone. So this system is called state tying. So with these techniques and systems, we spoke about the traditional system, but of course it's not the best working one, and there are improvements. And what else can be if not neural networks? Because neural networks are everywhere. Basically, we can replace all the components in speech recognition system with neural networks. Starting from the feature extraction, we can replace it, for example, with convolutional models, and we can also replace the acoustic and language models, and even the pronunciation model that is created by linguists. But for now, let's focus on a specific type where only the acoustic model is neural network. These are called hybrid models. These hybrid models are a combination of hidden Markov models and neural networks to combine all the advantages of these two powerful pattern recognition techniques. These are a great and big step forward, and they outperform the traditional methods. Let's speak about the neural networks in acoustic model. And for the acoustic model, we can use any type of neural network. For the fully connected networks, it's computationally intense and needs lots of parameters, even for reasonable feature size. And the convolutional networks that takes the advantage of locality and discovers the local information hierarchically, we have the opportunity to have more layers, deeper networks, and more complex functions. As speech is time sequence data, we can use not the 2D convolutions, but the 1D convolutions, and these are called time delay neural networks, TDNN. These TDNNs are the most commonly used one in hybrid speech recognition as an acoustic model. So let's speak about sequence-to-sequence data. So sequence-to-sequence tasks face the problem of data alignment. And especially for speech recognition, it's important to have the alignment of label in label sequence, for example, the phone to audio frame. And we need these alignments for each part of the audio, and this is a very big problem, and this is unavoidable for all the speech recognition systems. Also, there are end-to-end models that want to do all the functionality with neural networks, and they are using soft alignments. This means that every audio frame corresponds to every state, but with certain probability. This is soft alignments, and based on the implementation of soft alignment that end-to-end models are using, we can divide the end-to-end models into 3 groups. So the first one is the connectionist temporal classification-based algorithms. The next one is RNN transducers, and the last one, attention-based models. Let's speak about each of them. The CTC-based algorithms are using hard alignment, where every frame corresponds to only one state, and they are using this to aggregate and achieve these soft alignments. They are also making an assumption that labels are independent in label sequence. An example of this CTC-based algorithm is deep speech. So in the end, it's using CTC and beam search to get the font sequence. But it's important that this model uses another language model separate, an n-gram language model, and also this deep speech uses the number of decoded words in this frame, so it can get the final output. The next group are the RNN transducers. These networks are also using the hard alignments to get soft alignments, but unlike the CTC-based algorithms, they are not doing an assumption that labels are independent. And also, an important difference is that these RNN transducers have language model inside them. So you can see the difference of CTC-based networks and the RNN transducers, and you can see the prediction network in RNNs that are doing the work of language model. As the language model is about getting the probability of words from the previous phone or phones, we can pass the previous prediction, and with that we can mimic the language model. And in RNN transducers, having this language model, the prediction network, and also the joint network that will have all the information, we can have fully end-to-end models. The next one is the attention-based algorithms. So these algorithms are no longer using hard alignments to achieve soft alignments. Instead, they are calculating the probability of states, the soft alignments, directly with their attention mechanism. So this is the example of listen, attend, and spell, and this is one of the famous one in attention-based algorithms. It is encoder-decoder partied network, and the encoder creates a dense representation of features from the audio, and the decoder, taking these features, create a sequence of phones. Talk about these end-to-end models, and now it's time to compare this. So the highest accuracy you can see have the attention-based networks. But what's the disadvantage? A serious problem occurred when the attention mechanism needs the encoder. As this attention needs to be calculated for all the segment, we need to wait until the encoding phase is fully finished, so we can start running the decoder part, and it caused a big delay. The next one, and this is a really serious problem for ASR systems if you want to do it in streaming with real time. The next thing is the CTC-based algorithms that are not much accurate, you can see there, and the RNN transducer, which are the middle of these two algorithms. The disadvantage of this is the training procedure. So it's not easy to train RNN transducers because it's shown that it's better to pre-train the parts than start the whole training, so you can get better performance. We spoke about all the models, and now it's the interesting part, and we can speak about the challenges that we have faced. So as mentioned before, we need to run our system on device, on embedded device, and also we wanted to run the system for the conversations, daily conversations, and it's harder to train a model for these conversations than for structured data. The public data sets are mainly for structured data, and the amount of the data that we have and it's close to our target case was not enough. So we needed to do lots of data augmentations to get the data. The ones that we used are the commonly used speed augmentation, voice augmentation, and we used harmonic distortions. We added noises and voices of other people speaking in the background, and with this augmentation we get better results. The next challenge for us is the inference time. So the conditions are not suitable for running a real-time ASR system, and we need to choose really fast working ASR system. For us, it's also important to take into account the CPU load and also the memory that our system is going to use, because we don't have enough memory. Taking all these conditions, we chose a hybrid system. So this is our local optima, and it's not obvious that it's the best one, and for everyone that wants to use ASR system, it's the best solution, but it's the most suitable for our case. So there are reasons why we chose this. Before that, the disadvantages of hybrid models is the training. It's really hard and it's headache because there are so many stages, and you should train all these stages and combine the results. But it's worth because these hybrid models obviously need less training data. So end-to-end networks and all neural networks tend to overfit, and to get out of this, we choose the hybrid models. Also, there is a room for optimization. The traditional parts that I described, the HMM systems and the other ones, can be represented with weighted finite state transducers, and there are libraries that do optimization for these representations. And using this help us to get faster ASR system. So having all this, we chose the hybrid system, and yeah, that's all. Thank you for being here.
Questions? One question. You talked about the frames. Every frame has several probabilities.
Yeah.
Can you elaborate on that? How they calculate the probabilities for every frame?
You speak about this alignment. So in general, the traditional way when we calculate these probabilities with Gaussian mixture models, we start from alignment that if a word, for example, a cat, composes of the C, A, and T, and we have, for example, 3 milliseconds for the audio that this cat is in there. We divide it in 3 parts, equal parts, and you see that this is C, this is A, and T. But then with running and doing training of these Gaussian models and the neural network as well, we can get the exact alignment. So this is, we assume that it is A, but after training and seeing this, that these C fonts probabilities are closer to the A, we then remove the alignment of A and go to C. So this is a process when we start from an alignment and then continuously improving it.
So, except for the limitations that you mentioned, are there any other criteria which may contribute to choosing hybrid models instead of neural network-based models?
It's mainly the delay. For example, the attention-based models have this delay, and you need to have really powerful one device, and it's not very suitable for real time because the whole phrase should be decoded, and in every device, this part of the audio should be processed, and this causes delay. This is very noticeable in our devices, embedded devices, but it also can occur in other devices. Okay. There are the general, and also other criteria can be the generalization, how models generalize. For example, if you are training it for structured data, how it will be in conversations, and there are also tricks that language models being inside of the network or other than the network, it's different, and you can generalize well if you have, for example, it's said, I don't try it myself, but it said that if you have language model, another part, and you just can replace the language model, it's easier to generalize than if your network is fully end-to-end and you need to train the whole part.
How would you like the idea to make a tutorial that people that were absent from you can read your message and learn how to do ASR systems?
So it should be a very long tutorial because all these described parts are very high level and I missed lots of details that are important. Actually, there are good articles and maybe I can share the Medium articles and other things, and there are very good papers. So maybe with these papers we can create the tutorial. Thank you.
I have a engineering question. If your like kind of hybrid models, it's need some specific framework for inference. Like probably you cannot do just let's say with PyTorch, but as you do it on MPS device, you program them with C++ or something like that. What are the frameworks?
Yeah, so for hybrid model, it's the most commonly used one is the GALDI. It's combination. It's mainly for speech recognition, and there are very good recipes and other things, so you can combine and get these hybrid models.
Can you spell it?
KALD and I. The logo is the coffee sign.
Probably you have some kind of specific optimization for the platforms. Can you give some comment on this? I mean, like quantization, distributions.
The things that I described was about the representation, the weighted finite state transducers. But as the neural network is the acoustic model is neural network, we can do also quantizations there. So it's not as easy doing the quantization as in PyTorch or TensorFlow, where everything is also implemented. And honestly, right now we are working on that direction as well to quantize the model for our case and maybe get the bottlenecks where the network is not working fast. And so there are the implementations, maybe we can change something there. So we are now working on that direction.
Okay, so I guess that's it. Thank you very much one more time.
Thank you too.